Got a problem here. It's got lots of words, so I'll read it. The temperature at a weather station over 24 hours is given by the formula T of x, which is equal to minus 5 cos of pi on 12, x minus 3, minus a 20th of x minus 12 squared plus 7, where x is the number of hours since midnight. Find the average temperature from midnight to midday and also from midday to the following midnight. Okay. There's a lot going on there. I've got a formula which I'm not going to look too closely at yet that tells me what the temperature is at each moment, and that x is mentioned in hours, and then I want an average temperature. So I've got a function which is the temperature, so the average temperature would be the average value of that function. An average value is an integral divided by the width. So if I did the integral from midnight, which would be x equals 0, to midday, which would be x equals 12, and then divided by 12 because that's the width, that should be the average value for that bit, and the average temperature would be from 12 to 24, and then divided by 12 because the width is still 12. Okay, I really wanted to sketch this graph so that I've got an idea of what I'm expecting for my answers, and I think I'll use a machine to do that. This is Geogebra, and I'm just going to type in the formula. T of x is equal to minus 5 cos of pi on 12 times x minus 3 minus a 20th of x minus 12 squared plus 7. Okay, so it goes up and then down, rightio. I'm just going to mark the points of interest here. So midnight was x equals 0, and that's that point. And then midday would be x equals 12. And then midnight again would be 24 hours later. So they're the 3 points. So in this first zone, the average would be in the middle somewhere, maybe a little lower because it spends a bit more time low down. So maybe 4-ish. The average here on the other side, it goes up above 10. So I'm thinking maybe it's up here between sort of 6 and 8, somewhere over there. All right, I am expecting the average to be higher on this side than on the right than on this side on the left. So when I get my answers, at least I'll know what's sort of reasonable. Okay, I guess I need to figure out the integrals now. So I need to go back to using my paper. So I'm going to need a definite integral of this function from 0 to 12, and I'm going to need to divide by 12. And if I'm going to do a definite integral, I'm going to need an antiderivative of this thing. So that's a complicated sort of thing, and I think it might be a bit too hard to write it down in the middle of trying to find the average temperature. So I might do the antiderivative first. So the integral of t of x dx is the integral of minus 5 of cos of pi on 12 x minus 3 minus a 20th of x minus 12 squared plus 7. Okay, so the minus 5 is a constant multiplied on, so it'll still be there. Cos, just let me check. Yes, that's linear on the inside. So what I can do is do what I would normally do for cos and then divide by the constant that's multiplied by the x. So cos integrates, it would be plus or minus sign. Normally cos differentiates to give minus sign, so it integrates to give plus sign. So that's sine pi on 12x minus 3. But then I have to divide by this number, so that's the same as multiplying by 12 on pi. Okay. And the next bit, the minus a 20th is multiplied on, so it'll still be there. I've got linear to a power, so I can treat that as I would normally do powers. Power up by 1, divide by the new power, and then keep that as it is, but I'm also going to have to divide by the constant, which is a 1. Okay, so that's fine. And then the 7 would become 7x plus c technically. Now, if I'm doing a definite integral, I don't actually need that plus c. I feel like it'll be easier to give this a name so that I don't have to keep writing that formula out over and over. If this was a little letter, I'd normally use a capital letter for the definite, for the indefinite integral. So it's already a capital though, so I might use the next letter u. So let u of x be equal to minus 60 on pi sine of pi on 12 x minus 3 minus a 60th. 20 times 3 is 60. Yep, 60th of x minus 12 cubed plus 7x. Okay, now I reckon I'm ready. The average temperature, it's not just an average value, is it? The average temperature from midnight to midday is the integral from 0 to 12, because that's midnight and that's midday, of t of x dx, divided by the width, which is 12. So dividing by 12 is the same as doing a 12th. And then this integral would be an antiderivative, which we've just figured out and called u. So that would be a 12th of u of 12 minus u of 0. All right, so I'm going to have to plug this 12 and this 0 into this formula here. Like, I don't trust myself, that's really complicated. And I could use my calculator, but I think since I've already got Geogebra open, I might use Geogebra to do my calculations for me. Okay, so let me type in this new formula. U of x is minus 60 over pi times sine of pi on 12 times x minus 3 minus a 60th of x minus 12 cubed plus 7x. And then I need a 12th, that's a half, a 12th times u of 12 minus u of 0. And my computer says that that's approximately 2.349. Okay, a bit lower than I thought, but in the zone, still somewhere in the middle there. Okay. And then the average temperature from midday to the next midnight would be the integral from 12 to 24 of the temperature divided by the width, which is still 12. So that would be a 12th of the integral from 12 to 24. So I need to use an antiderivative, which we figured out is called u. So that would be a 12th of u24 minus u12. And I'll just ask my machine what that is too. A 12th, did it again, of u24 minus u12, which is 6.8508 approximately. So I've got that the average temperature from midnight to midday is 2.349. The average temperature from midday to midnight is 6.8508, which are in the ballpark of what I said they should be based on the information we had. Cool, nicely done.